From childhood, we are sold a very convenient picture of the past. Yesterday, man could barely hold a hammer. Today, he builds megacities, launches satellites, and models the world on supercomputers. The logic is beautiful, almost flawless. Except, beneath the beds of two European rivers lie structures that don't fit into this picture at all. For nearly 2 centuries, a tunnel has stood beneath the Thames that should have long since become damp, cracked, leaked at the seams, and turned into a museum legend about bravery and mistakes. But it stands. Beneath the Neva, another, no less strange, structure operated. In conditions where even modern technology often falters, 19th century people seem to know something about soil, loads, and materials that we no longer fully understand today. And here is where the most uncomfortable part begins. If these were simply geniuses, then where are the detailed answers? Where are the repeatable formulas? Where are the clear calculations that can be opened, verified, and replicated? And if there are no answers, then another question remains. Are we truly moving only forward? Or have some powerful technologies been left in the past, leaving us with only a beautiful story of continuous progress? Today we will descend beneath the Thames and beneath the Neva. We will examine not legends, but the joints, numbers, materials, pressure, air, water, and what is too stubborn to fit into the textbook version. And by the end, we will be left not with one sensation, but with something much more uncomfortable. Doubt in the very framework through which we were taught to view the history of technology. Right where you're watching from and subscribe to the channel. Thank you. Underwater, humans have always felt like strangers. Overhead is not just a ceiling, but an entire mass of water and soil, ready at any moment to remind us who is in charge. Therefore, the idea of an underwater tunnel still sounds like a challenge today, and for the 19th century, it seems something bordering on the impossible. Without electricity, without electronic sensors, without computer modeling, without the technology we consider essential for serious construction. And yet it is precisely there, beneath riverbeds, that structures appear which stand for too long and too confidently. Official history usually tells it like this. First there were primitive attempts, then engineering thought gradually grew, then the modern era arrived and brought everything to true perfection. But when you start looking not at the slogan, but at specific structures, a crack appears. Because some old constructions behave not like an early stage of imperfect technology, but as the result of a very precise understanding of the environment. They endure time, moisture, pressure, and changing eras as if their creators planned not for decades, but for centuries. And here the romance of the old world is not what's important. Not the pretty pictures with lanterns and bricks. The fact itself is important. Beneath the Thames and the Neva, underwater structures existed which, in the logic of linear progress, should be inferior to modern solutions in reliability, lifespan, and precision. But the opposite turns out to be true. The old, in many cases, appears more durable than the new. Not everywhere, not always, but often enough for the question to become uncomfortable. And that is precisely why we are interested not only in what was built, we are interested in what exactly is hidden there. Just tunnels, or traces of another engineering school that understood water, stone, and load far more deeply than we are accustomed to believing. Let's start with the Thames, because it is here that the structure often called the first underwater tunnel of the new era is located. And on paper, it sounds simply like an important engineering step. But in reality, it's much harsher. Before us is a brick structure laid under the river in the first half of the 19th century, when the very idea of such work seemed almost insane. A length of several hundred meters, 2 parallel passages, thick masonry, and most importantly, a location where water and soil should have done their work quickly and mercilessly. This tunnel's strongest effect is not in old books, but in real perception. Because underwater we expect to see traces of struggle, damp seams, separated lining, supports that long ago became part of a museum display. But instead, the structure creates a completely different impression. It doesn't look like a surviving accident. It looks like something that was made seriously and for the long term from the very beginning. And this feeling is far more dangerous than any loud theory, because it breaks the most convenient defensive phrase that the old builders worked crudely, and we're just lucky that some things survived to our day. This is especially sharp against the backdrop of our own time. We live in an era of expensive repairs, missed deadlines, constant maintenance, and promises that now the structure will be truly reliable. And then not a century or half a century, but 10, 15, 20 years pass, and already inspections, reinforcements, relaying, waterproofing, and replacement of cladding are underway. And next to this stands a 19th century brick tunnel. Not perfect, not fairy tale, but stubbornly alive. And then the question sounds different, not as admiration for the past, but as a challenge to the present. What exactly did they do such that their underwater work outlived generations, while our technologies often age right before our eyes? When the conversation turns to the Brunel family, everything is usually reduced to one word: genius. A convenient word, a beautiful one. But in engineering, it too often serves as a curtain, hiding the lack of a clear explanation. Yes, the idea of the tunneling shield was revolutionary. Yes, the organization of the work itself was astonishing. But the problem is not that someone came up with a bold concept. The problem is that this concept was successfully implemented in water-saturated soil, under pressure, in conditions where a mistake cost not money, but instant catastrophe. The tunneling shield in this story is not just an iron frame later romanticized in books. It is an entire mechanical system, massive, multi-sectional, designed for gradual forward movement. Workers excavated the soil literally piece by piece, and behind them, a new tunnel shell appeared almost immediately. That is, before us is not chaotic construction, but a very rigid rhythm. Soil removal, face support, advancement, immediate reinforcement. Essentially, here we already see industrial logic. Not "we'll manage somehow," but a sequence of operations where every error had to be accounted for in advance. And here is where the real awkwardness begins. Because the shield is not just an idea, it is metal, weight, assembly precision, part compatibility, load management, and an understanding of soil behavior. We are asked to believe that all this was assembled in a world of candles, manual labor, and extremely limited means of control. Perhaps it was, but then it demands even greater respect for the actual level of that engineering school. And if not, if some solutions were more complex than commonly told, then we are dealing not simply with an outstanding project, but with a system of knowledge that was later simplified into a legend about bold pioneers. And that is a completely different story. Any beautiful legend ends where arithmetic begins, because an underwater tunnel is not about inspiration, it's about pressure. Water above, soil around, an unstable excavation face ahead. And if the arch isn't calculated correctly, no amount of courage will help. You can talk all you want about engineering talent, but a tunnel doesn't survive on pretty words. It survives on numbers that either add up or kill the project. That's why old underwater structures disrupt our usual picture of progress. They weren't just built, they've endured their environment for far too long. Think about what underwater tunneling means in the crudest sense. Above you isn't emptiness, it's mass, constantly pressing down. Soil isn't static. Water seeks out weakness. The slightest inaccuracy in the arch geometry, in material bonding, in the sequence of work, and the whole system starts losing to its surroundings. Modern engineers hedge these risks with calculations, models, sensors, test bores, and complex machinery. And they're right to do so. But it's against this backdrop that the 19th century becomes not less strange, but stranger. because those builders had incomparably more modest means, and in places the result looks as if they missed less often than we do. Here one might object, we only see what survived. True, but even that argument doesn't remove the main question. For an underwater tunnel to simply last until our time, it must have been calculated from the start with a large margin of safety and a very precise understanding of form. Old masters may not have known our formulas in their modern form, but they clearly understood the behavior of arches, thrust, masonry, and environmental pressure, not at the level of guesswork. Otherwise, underwater construction would never have become reality. It would have remained a series of failures. So the next step is inevitable. If the geometry held, we must look at the material, because that's where the key to the most uncomfortable part of this story lies. Material. That's where old tunnels start to sound almost provocative. Brick by itself can still be explained. Lime mortar too. But when talk repeatedly circles around unusual strength in old masonry, about joints that behave too confidently, about a composition that continues to perform for decades under wet load, the story stops being merely architectural. It becomes chemical. And chemistry is ruthless. It doesn't yield to beautiful legends. Either there's something in the composition that explains the result, or there's no explanation. Around the Thames tunnel, discussions often mention reports of extremely high mortar strength and even the possible presence of mineral phases reminiscent of those associated with the durability of ancient Roman concrete. How accurate these assessments are in detail is another question. But the real nerve of the story lies elsewhere. Even if we dismiss sensational phrasing, what we're clearly not looking at is the trivial picture of thrown together on a whim and accidentally guessed right. We're looking at a material that resists dampness in time for far too long, and that already hints at precise formulation, at skill with additives, at understanding that underwater masonry is not at all the same as building a drywall on the surface. And here, for the first time, an alternative version of history stops being pure fantasy, not because it has proven anything, but because it points to a real zone of ignorance. We can't confidently say that old builders possess some mysterious, lost super science, but we can honestly admit something else. Their knowledge of binding compositions, of mixture behavior in wet environments, and of the durability of certain solutions may have been higher than we usually assign to them. And if that's the case, then beneath the Thames lies not just a tunnel. There lies a hint of a technological branch that was later either forgotten, deemed inconvenient, or simply left undeveloped. And that's only the first river. Now let's move to St. Petersburg. And here the convenient narrative of, well, fine, England had a unique engineering breakthrough, finally breaks down completely. Because the Neva is a different kind of water, a different riverbed, different logistics, and a different scale of risk. If the Thames can still be imagined as an exception, then a similar story under the Neva feels like a repetition of a theme that's far too inconvenient. Again, underwater work. Again, a harsh environment. Again, durability that looks stronger than expected. And once more, what we see isn't just boldness, but technique calculated for long service. The story of the Neva water supply tunnel is especially irritating to conventional logic, because here we're not talking about a museum passage built for glory, but about a real urban task. It wasn't enough just to pass under the river. They had to create a system that would work, supply water, hold its shape, and not turn into a constant point of failure. In other words, the object had to be not a heroic episode, but a reliable piece of infrastructure. And if it truly performed its function for decades and was decommissioned not due to collapse, but because new lines appeared nearby, that no longer sounds like a 19th century adventure. Here's the most uncomfortable part. When a similar level of engineering confidence appears in two different countries, with different specialists in different conditions, the version of a one-off miracle starts losing its force. What we may be looking at is not two lucky coincidences, but traces of a broader school in which understanding of underwater construction was more serious than commonly thought. And that means we should look next not at patriotic myths or national legends, but at the working environment itself. And here enters something that even modern projects approach very nervously: quicksand. Quicksand, a word that hides a very unpleasant reality. It's not just wet sand or inconvenient soil. It's a medium that at a certain point loses stability and starts behaving almost like a fluid mass. For underground work, it's a nightmare. You relieve pressure and the ground flows. Water appears and everything around becomes unstable. Any mistake in pace, in support, in the sequence of actions can instantly turn a construction site into a trap. That's why accounts of driving through quicksand in the 19th century sound as if someone is deliberately testing our credulity. The modern world knows how capricious such conditions are. When an underground project halts in difficult ground today, it's no laughing matter. It means millions spent on preservation, years of standstill, redesign, reinforcement, freezing, injections, emergency measures. And no serious engineer would call such difficulties trivial. That's why the comparison becomes especially painful. If in the 19th century they truly passed through such conditions under the Neva and created a stable, circular cross-section with durable lining, then what we're looking at is no longer a feat of luck, but the result of very disciplined knowledge of how to hold the face and how to quickly turn a dangerous void into a reliable shell. You could say we simply lack all the details. Yes, exactly. But that is precisely the problem. Because the outcome is visible. The structure existed and functioned. So, somewhere between the soil, the work process, the materials, and the organization, a solution was found that cannot be reduced to the phrase, "they just managed somehow." The history of underwater tunnels generally dislikes the word somehow. Here, you either understand the environment down to the smallest detail, or you get flooded. And the longer we look at such structures, the clearer it becomes. The old builders didn't just know enough about the dangerous ground, they might have known about it differently. And this leads us to an even more slippery topic: vanishing explanations. At this point, one usually wants to open an archive, find a complete set of blueprints, formulas, calculations, work logs, and calmly sort everything out. It's just that this is exactly where the investigation becomes particularly tense, because around a number of old underwater structures, there is just enough information to support the official narrative, but often not enough to fully answer the technical questions. There are general descriptions, there are historical overviews, there are reconstructions of events, but when it comes to the full set of engineering details, the picture often becomes fragmented. This doesn't automatically mean a conspiracy. Documents do get lost in history, archives burn, collections disintegrate, departments change, and some technical papers simply don't seem important to anyone until it turns out that the answer was hidden precisely in them. But for the viewer, something else is important here. The very lack of clarity works against the textbook version, because if the technology was fully understood, linear, and well continued into the present, then why are there so many gaps around the key decisions of the past? Why do we see the structures but not always see sufficient depth in explaining how exactly they achieved their outstanding longevity? And the more such gaps there are, the stronger the alternative hypothesis becomes. Not the one where everything is secretly classified forever, but a more down-to-earth and, because of that, even more unsettling one. Some knowledge might have simply fallen out of practice. Some formulas might have disappeared along with the schools of masters. Some documentation might have been too fragmented to be fully reconstructed later. And when knowledge is lost, legend takes its place. Genius, luck, and exception. It's just that under the Thames and under the Neva, too much looks not like an exception, but like the result of a system. And to test this, we need to look at the most earthly part of any underground construction: light, air, water, and logistics. You can argue about theories endlessly, But a tunnel isn't built with theories. It's built in a confined space where a person needs air, the work zone needs light, the ground requires continuous control, and the water is just waiting for the moment it's allowed to burst inside. Therefore, all the romance about building by candlelight works only until the first serious attempt to imagine this construction. Not as an engraving, but as a 12-hour shift underground, where dozens of people must see, breathe, remove soil, deliver materials, and maintain the pace without the right to prolong chaos. This is where one of the most uncomfortable questions arises. How plausible is the traditional, simplified picture of organizing such work? How much light was actually needed for precise masonry? How was air supply ensured? How quickly were smoke and soot removed? How was water pumped out after breakthroughs? How were bricks, mortar, metal, and tools delivered to places where every extra meter becomes a logistical problem? And the more you ask these simple, almost mundane questions, the less you want to settle for the school book version where everything is solved with the single word, courage. Courage existed, no one denies that. But courage doesn't replace ventilation, doesn't replace light, and doesn't displace water from a dangerous excavation. So either the system supporting the work was more complex and powerful than is commonly told, or we underestimate how meticulously they knew how to organize underground production in the 19th century. Both of these challenge our condescending view of the past, because behind the beautiful image of heroes with shovels might lie not a primitive construction site, but a very disciplined technological environment. And if such methods were applied not in one place, then what we have before us is no longer a coincidence. We have a series of coincidences that looks too much like a pattern. It is at this moment that the topic stops being the history of one amazing tunnel. Across 19th century Europe runs a whole chain of structures that, for all their differences, give a similar feeling: great length, difficult conditions, an underground or underwater environment, and a very serious structural lifespan. In some places, these are transport galleries, elsewhere, water supply solutions, elsewhere, large railway passages. But the common motif repeats again and again. The old world, which we love to imagine as technically naive, leaves behind structures that do not resemble naivety. Here it's useful to look not only at the sizes, but also at the nature of the result. These objects weren't just built and ceremoniously opened. They lived, worked, bore loads, water, time, vibrations, and changes in operation. This is especially clear in comparison with later giant projects, where there are already machines, calculations, control, budgets from another planet, and then leaks, reinforcements, fires, expensive maintenance, and endless upkeep begin. Modern engineering, of course, can do an incredible amount. No one denies that. But the old tunnels force an unpleasant admission. Not all progress means a longer lifespan for the structure. And so the conclusion becomes harsher. If similar solutions in spirit appeared in different parts of Europe, then we have no right to attribute everything to the magical biography of a single engineer. Before us is likely an entire construction culture, honed for longevity, margin of safety, and understanding of materials. Perhaps it was more expensive in terms of labor, slower in pace, more demanding of the craftsman. Perhaps that's precisely why it was later displaced by more standardized, industrial, and economically convenient methods. But underwater still lies the trace of the former logic, a logic in which they built not until the first major repair, but as if the object was meant to outlive its creators. And it is here that the conversation moves from the past into the present day. When an old tunnel outlives a new one, it's no longer just a question of history, it's a question of economics. Because the modern construction world is built around large systems, machinery, supply chains, services, regulations, standardized materials, payback periods, spare parts, warranty cycles, and entire industries that earn money from upkeep. In such a system, a method that requires more craft knowledge but promises extreme durability might be unprofitable not because it's bad, but because it fits poorly into the logic of the modern market. This leads to the most uncomfortable hypothesis of this episode, that some old approaches disappeared not because they were completely useless, but because the world chose different priorities: faster, more mass-produced, easier to replicate, more convenient to integrate into large industrial chains. This is not a conspiracy theory. This is the ordinary story of civilization. Useful things vanish not only when they are banned, they also vanish when there is no one to pass them on, when a craft splinters into separate industries, when knowledge ceases to be a living tradition and turns into a museum caption labeled "the world's first." This is why even small attempts at modern reconstructions of old methods are so important. When enthusiasts, researchers, or engineers test old lime mortars, shield tunneling ideas, or masonry principles on a small scale, they do the essential thing. They bring the conversation back from myth into practice. And every time it turns out that old solutions are not as primitive as commonly thought, the system feels uneasy. Because then it's not just the past that is called into question. Our very notion of what counts as modern, rational, and progressive is also called into question. After that, only one final step remains: to ask directly, what is truly hidden beneath the beds of the Thames and the Neva? So, what do we have in the end? Beneath the Thames, a tunnel that has survived time and water with uncanny resilience. Beneath the Neva, a submerged structure that in a harsh environment appears too sophisticated for its era. Surrounding them are questions about the materials, the calculations, the work organization, the ventilation, the soil behavior, the completeness of the surviving documentation. Each oddity can be explained away individually, some by craftsmanship, some by a safety margin, some by luck. But when all these oddities form a single chain, a feeling emerges that we are not looking at a set of miracles, but at the trace of something greater. I am not asking you to blindly believe in one single version. There's no need to turn history into cheap mysticism. Something else is far more interesting. To honestly admit that the past was more complex than the schoolbook schema of from primitive to perfect. Perhaps a strong engineering school existed, part of which dissolved along with its masters, its archives, and changes in the industry. Perhaps some materials of the past worked not by miracle, but by precise formulations that later stopped being replicated. Perhaps we lost not a super secret, but an entire culture of building for the centuries. But we lost it so thoroughly that now even the very fact of its existence sounds uncomfortable to us. And then the main mystery of these objects changes. Hidden beneath the riverbeds are not just brick, metal, and old vaults. Hidden there is a blow to a very comfortable illusion, to the belief that each succeeding generation necessarily knows more than the previous one in every way and always. No, sometimes the past can do things the present can no longer replicate with the same calm assurance, cheapness, and longevity. Sometimes knowledge does not grow in a straight line, but breaks, disappears, becomes simplified, and returns in a different form. So, after this episode, look around at the old tunnels, cellars, conduits, embankments, arches that stand in defiance of time and our proud narrative of progress. And if you appreciate investigations like this, be sure to like, subscribe to the channel, and hit the bell. Because next, we will go even deeper, to where the history of technology begins to sound nothing like what we were taught.